Hey, I'm Omer Yair, and in this video I'll be presenting our 2024 CVPR paper, Uncertainty Visualization via Low-Dimensional Posterior Projections, and in a minute I'm going to explain exactly what that means. This is a joint work by myself along with Elias Nehme and Michaeli. So, without further ado, let's dive right in. Let's begin by laying down the problem. An inverse problem begins with some original sample X that undergoes some forward process which creates a distorted version of it, Y. We would then like to devise some backward process which could reconstruct X back from Y. However, the problem is that in most cases there exists more than one solution, or if to be more precise, there exists a distribution of possible solutions known as the posterior. In theory, it would be nice if we could simply provide this posterior to users in order to present them with the entire range of plausible solutions. However, in practice, since this is a complex distribution living in a high-dimensional space, we cannot directly visualize it. Therefore, we need to seek some method to somehow provide a simplified version of it to the user. There are several ways to try and tackle this problem, and in this work, we have chosen to extend an existing method known as NPPC, which was introduced in NeurIPS 2023. The idea in NPPC is to train a network to directly produce the first few principal components of the posterior for every given sample. The motivation for this comes from the fact that these principal components capture the direction in which the posterior varies the most. Therefore, by allowing users to explore the samples along these directions, we can provide them with a better understanding of the range of possible solutions. In this work, we've taken this idea one step further. Instead of just presenting users with samples along these principal components, we wanted to also be able to convey to them the probability related to each sample. The way we do so is by projecting the high-dimensional posterior into a lower 2D plane defined by these principal components. We refer to this distribution as the projected posterior distribution, or the PPD for short. By presenting this PPD to users, we can help them gain some intuition regarding the full range of plausible solutions. So, the overall process which we suggest is as following. We start with a given distorted image Y, and we then utilize some existing method to extract a 2D subspace. We define this subspace by a center point x0 and two directions w1 and w2. In this work, we've used the MMSE estimator as a center point x, and we've used the NPPC method to produce the two directions w1 and w2. Given this subspace, we would like to focus from here on only on the projection of samples upon it. We define V to be the new coordinates of the projected samples. By using this notation, we can define the PPD as the conditional probability of V given Y. So now that we have defined the PPD, what we would really like to do is to have an efficient method for quickly producing it for every given input Y. This could be achieved by training a model to do so. In this video, I won't dive into the details of the model and how we've trained it, but if you're interested in that, I encourage you to check out our paper. I would, however, want to go over some of the results we've got using this method. Starting with MNIST, we've applied our method to the problems of in-painting and denoising with a very high amount of distortion. In these problems, it is common to have a multimodal posterior due to the fact that the different digits tend to be spatially separated in the sample space. We can see that the PPD is able to reflect the multimodality and the non-trivial shape of the posterior. We can also see from these figures how different areas and modes in the PPD correspond to different solutions of the problem. When moving to more complex inverse problems, we found that the PPD tends to be unimodal and usually has a much simpler form. Apart from this difference, we get more or less the same results where the PPD could be used as a useful tool for better understanding the range of plausible solutions. In the example here, we can see the PPD for an ImageNet colorization problem. And here we can see an additional example for the PPD of a Celeb A in-painting problem of the area around the eyes. In addition, we've also tested our method on nonlinear inverse problems in which one microscopy imaging method is tasked to be converted into another. In this example, it can be seen how the PPD can convey the fact that different solutions might contain different amount of cells. If you're interested in seeing some more results and playing around with an interactive version of the PPD, you are welcome to check the interactive website we've created for that. You can find the link to the site either on the project's GitHub page or in the description below. If you found this work interesting, please check out our paper. I really hope you've enjoyed this video. Take care and goodbye.